Can everybody hear me up there? All right. So we mentioned the Cook's theorem showed that satisfiability is NP-complete. And shortly thereafter, Karp showed lots and lots of other problems are NP-complete as well, including graph cliques, set covers, Hamiltonian cycles in graphs, graph colorability. We'll talk about this one in much greater detail today, actually. Partitioning problems, knapsack problems. All these problems are NP-complete in the sense all problems in NP reduce to each one of those. And so each one of those is as hard as satisfiability, namely the hardest problem in NP. And so they're all on equal footing. So there was nothing special really about satisfiability per se, even though Cook showed that that's the first problem to be NP-complete. Something had to be shown first historically, right? And that was satisfiability. But that was just an accident of history. So Cook opened the floodgates, and Karp showed that that phenomena of NP-completeness is ubiquitous. It's everywhere. So bin packing is NP-complete, even in one dimension, never mind 2 dimensions or 3 dimensions. Steiner trees, NP-complete, and that problem is very ubiquitous. Every time we want to interconnect things in a building or with streets on a map or with fiber optic across the nation, that's a Steiner tree problem. So connectivity problems of all kinds are NP-complete. Traveling salesman problem, we mentioned that. That's NP-complete as well. And graph colorability is the problem of trying to paint a graph with different colors such that no 2 adjoining edges, vertices share across their adjoining edge the same color as each other. So yeah, neighboring nodes must have different colors. And then we talked about Cook's paper. We actually showed the entire paper. And here he shows about 20 problems or so, all NP-complete. Long laundry list where satisfiability was the first, but there's about 21 others, and now we know there's literally thousands and thousands. New ones are being shown to be NP-complete every single day and every single week. But this is a seminal paper that showed the ubiquity of this phenomenon. So it's really a earth-shaking revelation. So the idea of these reductions, you reduce a problem to another problem, and then if you had a solver for the other problem, you can solve the first problem effectively. That's sort of the notion of a reducibility or a reduction. And let's talk a little more specifically about decision problems versus optimization problems. So in a decision problem, you just say yes or no. So given a Boolean formula, is it satisfiable? So you give a Boolean formula, and your answer is just yes or no. And that's a hard problem, satisfiability. But it'd be a little bit harder, at least seemingly harder, if you're actually asked to give the satisfying assignment, not just say yes, one exists, but not actually give it. So more decision problems in terms of these NP-complete problems, given a graph, is it 3-colorable, yes or no? So for example, this graph I give you without the colors, and you say, yeah, it's 3-colorable. Of course, there is also a coloring, but that's not what you're required to do. Just tell me if it's colorable or not colorable using 3 colors only. I give you a graph and an integer k and say, is there a k clique in there? Like, is there a 5 clique in here? But I don't show you where it is, like it's nicely painted green here. I just ask you if there is or there is no k clique there for k is equal to 5 in this example, but arbitrary k in general. So here's the corresponding optimization problems. Is not just tell me if it exists, but actually tell me what a solution is. Give me a solution. So given a formula, find a satisfying assignment that makes this formula true. Or find a 3-coloring that allows you to 3-color this graph. Or find a 5 clique in this graph that I give you and show me where it is. Now, certainly the optimization problem is not any easier than a decision problem. Because if I give you a solution, you know that there is a solution exists. If nothing else, it's a solution that I give you. And there could be other solutions too. Solutions are not unique. There can be many satisfying assignments. There can be many cliques. There can be many ways to color a graph. But is it any harder? That's the more insightful question. Well, certainly it's not any easier, but is it actually harder? It turns out it's not any harder either. It's the same level of difficulty modulo polynomial time, and usually a very low order polynomial. So the theorem we're about to prove is that solving a decision problem, it's just as hard as solving the optimization version. So the easy version of the easy half of the theorem is that solving a decision version is not hard in optimization, because optimization immediately implies existence, and therefore the decision is yes. The other direction is not easy to see, that if you can solve the decision version, you can also efficiently, you can also solve the optimization efficiently always, no matter what, for any problem in NP, and in particular for the NP-complete problems. How many understand the issue here? Okay. We're about to prove it. So the proof is not that hard, right? So again, a decision problem is in P if and only if its optimization version is in P. So the yes-no version is just as hard as finding the answer, modulo polynomial time. Okay. So how do you do it? How do you build an optimizer from a decider? And we've seen problems like that all along. In fact, the homeworks have problems about building optimizers from deciders and deciders from optimizers. And we did it in the context of decidability and undecidability. How many remember those discussions, right? Now we're about to do it in the context of NP-completeness, where we're watching the clock. We're watching the time consumed while we compute. We can't just do it any really arbitrary way, but we want to do it in an efficient way, build a decider from an optimizer or an optimizer from a decider efficiently. So let me show you an example of how that might work. So let's say you have a satisfiability decider. He just takes a formula, any formula you give it, and he says yes or no, it's satisfiable or not satisfiable. All it does, it only takes polynomial time to do it, it's efficient, and it's always correct. Right? So it's always a finite time, and in fact, polynomial time says yes or no always correctly. So if you ask it, what is a satisfying assignment for this, it can't answer it. What is a satisfying assignment? All it can tell you is yes or no, it has a satisfying assignment or not, but not actually give it to you. How does it figure it out? That's its business. That's not your business. It just says yes or no, and you can count on its output being correct every single time. So how do you build from a decider an optimizer? Well, let's say you have this formula coming in the door, and you want to know what the assignment is, and all you got is a decider that tells you if it's satisfiable or not. So you can ask it a question. You can ask the decider a question. You can take this formula P, color-coded purple, and ask it P and X. So you're modifying the formula P to a formula P prime that says P and X. So it's another satisfiability instance, slightly different than the first because we're ANDing an X with it, along with the original form, P. And then watch carefully what it tells you. If it tells you it's decidable, if the satisfiability decider tells you it's satisfiable, P and X is satisfiable, that gives you a bit of information that you didn't have before. What does that tell you? If the decider tells you that P and X is satisfiable, what information do you now have? Yeah, it tells you that there exists some satisfying assignment where X must be true in that satisfying assignment. How many get that? Otherwise, P and X wouldn't be true. Wouldn't be satisfiable if there was no satisfying assignment where X was true, because X is ANDed right here alongside P. So if there's a satisfying assignment for P and X, there must be a satisfying assignment for P where X is true. Otherwise, P and X wouldn't be true if one of those didn't exist as a satisfying assignment for P, because X is ANDed right into it like this. And an AND can only be satisfied, can only be equal to true if both things are true. And one of those things is the X. So the X must be true in some satisfying assignment. So if the decider says yes, you have this bit of information now. And by the way, if you say P and X prime and the decider says no, you have the exact same piece of information again. So this is an equivalent question. A yes on a P and X is the same as a no on a P and not X. Right? Both lead to the same conclusion, and that conclusion is that X must be true in some satisfying assignment. There exists a satisfying assignment where X is not for all assignments, all possible assignments, all bets are off. But for some satisfying assignment, X must be true in that assignment. All right, if it says no, or if the other says yes, by the way, I'm drawing both of them here, but you just need to go with one of them, not with the other. If you do it with one, you're good for the other. You just negate its answers, right? If P and X says no, what do you know about X in some satisfying assignment?
Well, I have a question. Isn't the no answer more specific than the yes answer? Because if it tells you yes, isn't there still a chance that X could also be false? Whereas if no, then you know it has to be the other one.
Yeah, that's true. But I'm showing you kind of both cases anyway. Let's just go with the top case. Ignore the bottom case for now. We'll get back to that if necessary. But yeah, you're right. So if P and X says no, what do you know about X in some satisfying assignment?
It must be false.
Must be false, right? In other words, by asking this decider questions one at a time, you're forcing it to reveal values of these variables in some satisfying assignment, and you just keep going, right? So if P and X, says no, P is not satisfiable. If P and X says no and P and not X says no also, neither one is satisfiable. That means there is no satisfying assignment. Okay. And if one says yes and the other says yes as well, that's kind of an interesting case as well. If P and X is satisfiable and P and not X is satisfiable as well, what do you know about X as far as satisfiability goes in this formula P?
There's satisfiability with X being true and
Yeah, it's satisfiable with X being true or false. It doesn't matter. So X, in some sense, is a what kind of a variable in terms of digital logic? You probably ran into that in digital logic class. How many of you have taken digital logic, Karnaugh maps, and so on? So what kind of a variable is X here in that sense? Take a wild guess. You've heard that phrase before. It's a don't care kind of variable. It doesn't matter what it is. If it's true, you're fine. If it's false, you're fine also. It doesn't get involved in the output of the formula or the computation of the assignment, of the formula. So X is a kind of don't care variable. So based on a decider, and if you ask it a couple of questions, you'll know if X is true or X is false in some satisfying assignment. And let's say now you know whether X is true or false in some satisfying assignment, because it ain't going to be one of those. Because if you get a no here and a no there, you can just say, no, it's not satisfiable, P is not satisfiable, and stop and never continue, and you'll be right. And if you get X is a don't care, you can just forget about X and keep going for the other values. If X is a don't care, it doesn't mean that P is satisfiable. It means that it's satisfiable or not satisfiable regardless of what X may be or may not be, true or false. Okay. So now that you know whether X is true or X is false in a satisfying assignment, because this decider told you yes or no, what do you do next? Because now you just got one variable, X. So in one word, what do you do next? Somebody who hasn't spoken yet today. Let's get more people participating. I don't want to call on people and put people on the spot, but I want more people to participate, other than the 3 or 4 or 5 that just keep impressing me, and that's great, but others should feel the rush of speaking up, and it's you get points for courage just for saying anything, really, yeah.
You just do the same thing with all the variables.
Yeah, you keep doing the same thing over and over again. So you repeat what you just did with a different variable y, and then repeat that with a different variable z, and so on and so on. And each time you're squeezing one more truth assignment for one more variable out of this decider, despite the fact that this decider can't directly give you a satisfying assignment, just tell you whether the formula is satisfiable or not, yes or no. How many see what's going on here? And so you iterate, the magic word, iterate, or repeat, do it repeatedly. Right? Think about it, if you couldn't iterate in computer science, the field would be useless. If every piece of code will only execute once, not many times. It's a lot of trouble to just do something once. You might as well do it by hand. Okay, so what we're doing here is we're building an optimizer from a decider. You were given a black box subroutine decider, and you've just built an optimizer for it by pulling this trick, asking it repeatedly what it's designed to answer, whether a particular Boolean formula is satisfiable or not. Question?
If X is a don't care, don't you still need to set it to something? For example, if your input satisfiability is X or Y, then technically if you run this operator, it'll be a don't care should both.
Good question. He's asking if X is a don't care, shouldn't you set it to something and kind of modify the formula with whatever you decide to make X, because you have a choice, because it's a don't care? You don't even have to do that, because this formula here, P and X, let's say it's satisfiable. P and X, the decider says yes. Then next, are you going to say P and Y? What you can say is P and X and Y. Because if X, P and X was satisfiable, test P and X and Y, or P and X and not Y. And then for the Z, go P and, so let's say the Y is not satisfiable, then say P and X and not Y and Z for the next iteration and so on. So you just keep tacking on the variables. You don't even have to worry about assigning to anything specific. You just know that it doesn't matter. Good question. Any other thoughts so far? This is a very general technique. How many encountered this somewhere in your life, this situation before, perhaps as children? When? When did you seen it or encountered it?
I mean, if you're trying to figure out the truth of a statement, you can always look at the negative statement and just treat it out.
Yeah. What do you say?
You're trying to decide what's for dinner. You ask your stomach whether it would like something or not.
Okay, you ask your stomach about dinner. Okay, let me make the question more specific. There's a children's game that most of you probably played that uses this exact same algorithm. What is the name of the game? Mastermind? There's aspects of this in many games. But this game, just plain and simple, as is on this slide, this algorithm. 20 questions. How many played 20 questions before? Yeah, most of you, right? It's a very common children's game. This is 20 questions. How many get that? So we're playing 20 questions with a decider. And that builds us an optimizer. Because what is 20 questions? You try to decide what object am I thinking about. So you're extracting my answer bit by bit, because all I can say is yes, no. I can't tell you it's a giraffe. But you can start asking, is it an animal or versus a vegetable? And I'll say, yeah, it's an animal. So you ask me, is it an animal? And I'll say yes. Next, you'll say, is it a vegetable or a mineral? And that really narrows it down. Well, narrows it down from millions of things to only hundreds of thousands of things, but still narrows it down by one bit. It's not an animal, it's a vegetable. It's not a mineral, it's an animal. So now you know it's an animal. So you're not going to ask me if it's a diamond or a quartz or ruby. You're going to ask, is it a mammal? And I'll say, yeah, it's a mammal. Well, that rules out sharks and a whole bunch of other invertebrates and so on. And then you're going to ask me, okay, does it have 4 feet, 4 legs? And I'll say, yeah. Well, after 17 more questions, you'll know it's a giraffe rather than a zebra or a kangaroo or a mouse or whatever. How many objects can I differentiate with 20 questions? How good, how much resolution does this game have on the space of objects?
If you play perfectly,
2 to the 20, if you play perfectly. So it's a big if, but children are pretty good at this. I mean, adults, even better. Computers, really good. So yeah, you can differentiate 2 to the 20. How much is 2 to the 20, just as an integer? Quick, say it quick. Not quick enough. 2 to the 20 is what? How come I don't hear it yet? You should all be screaming the number. 1 million, yeah, roughly. Remember we had discussions about powers of 2 and arithmetic numeracy, and especially about powers of 2. you should be able to say the powers of 2 really quick and know what you're talking about, right? You should say, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 4096, and then, you don't have to say exactly the rest, but, approximately you should say, 2 to the 10 is 1024, so 2 to the 20 is square that, so you get 1024 squared, that's a million plus, it's a million and change, right? 2 to the 30 is 1024 cubed, that's 1,000 cubed plus change, 1,000 cubed is a billion, so it's a billion plus change, and so on and so on. So 32 bits represent 4 billion, right? So anyway, those things just roll off your tongue, right? If they don't, people will wonder how deep of a thinker you are, how versed of a computer scientist you are if you have to kind of wonder or scratch your head when it comes to powers of 2, especially small powers of 2. So, I mean, we don't expect you to know right off the top of your head what 2 to the 64 is, but it'd be nice if you knew. And 2 to the 64 is, 4 billion squared. So it's 16 billion billion, roughly, and change, right? But you should be able to do that quickly. Okay, so 2 to the 20. So this game can differentiate a million things if you just have 20 questions. And this is basically implementing 20 questions algorithmically in general for any problem in NP. Because you can do this about not just satisfiability, but about any other problem in NP. How could you do it about other problems in NP now that you see the idea? If I ask you to do this for graph colorability or cliques or Steiner trees or packing or binning problems or knapsack problems or traveling salesmen, how will this work? What's that? Swap out the x. So, but now we're talking about graphs, we're talking about cliques, we're talking about trees. It's no longer, so what's the general technique that would work?
Okay, for a knapsack, you take one element, you put it in the knapsack, you subtract that from the size of the knapsack, and then you ask it again.
Yeah, so for every problem, you can sort of pull the same trick with a similar mechanism. Try something, if it doesn't work, subtract it out, try something else, and eventually you'll know which one is part of your answer, whether it's knapsack or traveling salesman, an edge in the tour, if it's a TSP, traveling salesman. But give me a more general technique that doesn't rely on a special case solution for each new problem. What allows me to say I can pull this trick for every problem in NP? I can always turn a decider into an optimizer, no matter what the problem is, and not go through a long list of tricks about how to do this individually for every problem. Because guess what? There's an infinite number of problems. So what, are you going to give me an infinite number of different algorithms or techniques? Do it in one fell swoop. Knock them all down with all for the price of one. Yeah. Yeah, it's about the reductions. Remember, all of NP reduces to SAT. And all these problems are in NP, right? All these problems that we saw before, satisfiability and graph colorability and cliques and knapsacks and packing and scheduling, they're all problems in NP, and we already know how to reduce all of them to SAT. How do you reduce all of NP to SAT? 2 words? Cook's theorem. That's what Cook did in his famous theorem. We went through that. So you can exploit Cook's theorem here and use this 20-question trick to apply to any problem in NP automatically, right off the bat. Just drag it through the reduction in Cook's theorem. Now, that's not to say that when you look at specific problems like this, there's not some shortcut bypassing Cook's theorem. And here we didn't use Cook's theorem directly. We just kind of played 21 question, in this specific way with the formula ended together with the variable and so on. But you can do this for graphs specifically, or generally use Cook's theorem. Right? Or for any other problem in NP, just use Cook's theorem is enough to show that all of NP could be treated this way through the reductions. And by the way, what allows us to say that this optimizer runs in time polynomial of this decider's runtime? Because that's important. If the decider runs in polynomial time, then so does the optimizer. What enables us to make that bold assertion that is not immediately obvious, or at least needs to be said, it's not automatic?
Because they're all n variables.
Yeah, it runs in time linear times the time of the decider. Using the decider as a subroutine, how many times are you calling the decider? N times. N is roughly the instance size of P. P has n variables. And so if there's n variables, you call the decider of that n times, and then you got it. So if the decider runs in some polynomial time, this optimizer that we just constructed from the decider runs in time n times that polynomial, which is still another polynomial of maybe degree a little bit higher by one exponent, but that's okay. That's still a polynomial. So that's important. So whenever you have an efficient decider, you can build an efficient optimizer from it automatically, for sure, always, for any problem in NP. Question?
How would you go about finding a reduction from any other kind of problem to SAT?
Yeah, so how do you reduce any problem in NP to SAT? Well, that's what Cook's theorem does. So Cook's theorem takes an arbitrary Turing machine computation in SAT, non-atomistic polynomial time computation, and reduces it to one big formula that's satisfiable if and only if that computation accepts its input, right? So Cook's theorem does that for you. Now,
Actually tells you what the function point is.
yes, it produces a formula from an arbitrary Turing machine, an arbitrary input. Now, Cook's theorem was a big, theorem. We took a lot to come up with that, and even explaining it here took half an hour or whatever. But after you are okay with the theorem, you could use it in a sense that it reduces everything in NP to satisfiability in polynomial time, and it gives you a general reduction of arbitrary Turing machines that run in polynomial time, non-deterministic Turing machines, maps them to SAT in a membership-preserving manner. Yeses map to yeses and nos map to nos. Members map to members and non-members map to non-members. So accepting computations map to satisfiable assignments, and no computations or rejecting computations map to non-satisfiable formulas. And if you had a decider for the satisfiability problem, you'd have an automatic, quick algorithm to determine what an arbitrary non-deterministic Turing machine does or doesn't do for a given input, as long as it runs in polynomial time. Question?
About the generalization of this optimization scheme using reduction, doesn't that not actually answer the optimization question for other problems? Because if you reduce another problem to SAT, and then you do this optimization thing, you get the answer. The answer you get is an equation or a set of variables, true for X, false for Y, and so on. That's not the original question, which is what is, say, the colors that go in the graph.
That's a excellent question. All right, so let me unpack it for you a little more. So he's asking very incisively, the other problems in NP that we try to push through Cook's theorem to reduce to satisfiability and then convert the decider into an optimizer, how will we get the answer for those? Well, we'll formulate that problem as a optimization anyway. In other words, I'm going to take the question of if I want to find, say, a traveling salesman tour less than 1,000 units long among some very large, million-node graph, I can come up with a non-deterministic polynomial time algorithm that will do that quickly. Not just tell me that the solution exists, but actually find it. How? Pick the first node in the tour non-deterministically out of all n nodes. Pick non-deterministically the second node in the tour out of all n nodes, and so on and so on, until you find the last node in the tour and then connect it back to the beginning, and then measure the size of a tour by adding up all the edges in this tour that I guessed non-deterministically by picking non-deterministically each edge one at a time, and then compare that to 1,000. And if it's less than 1,000, I raise my hands in victory and say, yeah, I got it. There's the tour, less than 1,000. I just described a non-deterministic algorithm to find a short tour, a tour of less than the size of 1,000. How many are good with that so far? Okay. And that's the one I'll convert to satisfiability that will tell me whether that computation ends up in success or not based on whether the formula has a satisfying assignment or not. And they'll find me the tour. Now, another question might be, how do I know that 1,000 is the right threshold for a traveling salesman instance? Maybe there's something of size 500. Do a binary search on the goal. So I can start with 1,000, go to 500, then to 250, and if 500 is too little and there is no solution, I'll go to 750 and so on and so on. Eventually, I'll know exactly what the optimal is. So I can always do a kind of a quick converging binary search on whatever goal I need, whether it's the length of the tour or the number of colors necessary to paint a graph, or whatever. So let's leave that alone for now. There's a lot more things I want to cover. But you can do that in general. So one of the upshots of this theorem is that instead of talking about optimizers going forward, suffice it to only talk about deciders. And that makes our job easier, at least conceptually, because deciders only do one of two things. They either say yes or they say no. They don't do anything else. They always halt with a yes or a no, so it's a Boolean function that they're computing. They don't have to give some complicated object like a coloring or satisfying assignment or some traveling salesman tour or a clique, or they just say yes or no. It has a clique, it doesn't have a clique. Yes, it's colorable, no, it's not colorable in 3 colors or whatever. So from now on going forward, all we got to worry about is deciders, and all the results will automatically apply to optimizers as well because of this 20 questions kind of situation. So whatever we can show about deciders or give algorithms for deciders or prove what deciders can or cannot do efficiently, that will automatically apply to optimizers as well. How many can see that? Because you can always build an optimizer from a decider using this 20 question technique. There was a question, yeah.
So the optimization problem is satisfiability. What does that mean? Is it like a yes and no?
So the optimization version asks for an actual answer, for an instance of an answer. So just like here, so here are decision versions of the problem, and here are optimization versions of the same problems. Well, so the problem often comes in the form, is there a solution less than this cost? And the answer is either yes or no. So, but the optimizer actually have to give you a solution less than the cost, actually hand you a solution, not just say, oh yeah, one exists.
So my question is, like, you can't really compare the cost of one solution to another in a way. Like, is it a yes and a no? Like, it's just bits, like 1 to 0. So how do I make sense?
Yeah, so what you would do is convert the computation that gives you a solution, that finds a solution, and says, there is a solution of less than, something, and there it is. And it builds a Boolean formula that tells you if that computation terminates with a yes. In other words, the formula essentially kind of simulates the computation in a sense, right? And so what this is all saying is that finding a solution is not any harder than determining whether a solution exists. So let's go forward a little bit, and if there's more questions later, we'll circle around again. This is important, but I don't want to spend most of the period on this slide. Okay. So we'll see instances of how this works basically. So the graph clique problem. Find a clique of size k. So I give you a graph and an integer k. Find me a subgraph, a fully connected clique of size k, where everything is connected to everything else among these k nodes. We're about to prove it's NP-complete. So we're going to give some reductions now, specific reductions for some of these classical problems, showing that they're NP-complete. So here's how we can reduce 3-sat to this graph clique problem. So for example, here's an instance of 3SAT. Here's a formula, and the question is it satisfiable or not? We don't know, but we're going to convert this to a graph in the following way. We're going to take each clause and create a group of vertices in this graph. So these are nodes in the graph, but they have variables per clause, and it's color-coded. So this red clause gave rise to these 3 nodes in this graph. This green clause gave rise to these 3 nodes in the graph, and this blue clause gave rise to these 3 blue nodes in the graph, and so on. So for every clause, I'm creating a set of nodes in the graph. Okay, and then I'm connecting every node with every other node in the other groups that it's compatible with, right? So if x here could be true, that's compatible with y prime being true, regardless of what x naught is, right? And then z being true, and so on. So I'm creating sort of a compatibility graph, if you will, an intergroup compatibility graph. And I'm going to put all the edges in there that are compatible with one another in terms of variables in these clauses. What can live with other variables in terms of the whole formula being satisfiable or equal to true. Now, once you do all this, you observe that a 3 clique in this graph, by the way, no green node is connected to another green node. So any triangle in the graph has 1 red node, 1 green node, and 1 blue node in it. And generally, if you had more clauses, you'd have more groups. So you could have a purple clause and a purple group here, and every red node, every green, every 4 clique at that point will have a red node, a green node, a blue node, and a purple node. So the point is the K clique in this graph corresponds to a 3-stat solution in the original formula. So for example, if you focus on this clique here, on this 3 clique here, the X, the Z naught clique, that implies that X true, Y false, and Z false is a solution in the original formula. And if you plug it in, you'll see that that works. X is true will make this first clause true. Y false and Z false will make the second and the third clauses true, and the whole thing becomes true. So it is satisfiable under this assignment, which corresponds to this purple clique. And the same true for any other clique. So there's many other solutions here. Take any triangle here in this graph, and that corresponds to another solution that will satisfy the original assignment. So we've reduced SAT, in fact, we reduced 3SAT, but it's SAT in general, to the graph clique problems. If we have a solver for graph cliques, we can exploit it into solving SAT for us by first constructing this graph and then looking for a clique in this graph, which would correspond to a satisfying assignment in the original formula. So this means all of NP reduces to not just SAT, but to graph clique through SAT by composing the 2 reductions. First, Cook's theorem reduces all of NP to SAT, and then our reduction, of course, reducing SAT to 3SAT. How many remember our reduction reducing SAT to 3SAT? Long clauses became short clauses, and there was more of them. And then this reduction here, reducing 3SAT to graph clique. Compose these 3 reductions, each one being in polynomial time, and you get one end-to-end giant polynomial time reduction of all of NP to clique. And in fact, that's what Karp does in his paper for this problem. So I just kind of unpacked one of his 20 or so proofs from his paper. And he also gives you the proof for all of SAT reducing to 3SAT, which we already discussed last time. So that's an example of showing another problem being NP-complete. Now, this proof is relatively short, right? You take the whole proof is right here via this example. I mean, this generalizes to arbitrary formulas. You just get bigger and bigger graphs and larger cliques, but it's an if and only if, and it works pretty nicely. So what we've done here is we exploited a solver for the clique problem into being a solver for SAT. And so if you wanted to solve graph cliques efficiently, that would automatically give you an efficient algorithm to solve SAT via this reduction, right? So that's why the graph clique problem is NP-complete, because everything in NP reduces to it. And of course, we have to show the other part of NP-completeness, right? You have to show everything in NP reduces to it. And what's the second part you got to show, the second condition? It's a minor one, but that is in NP itself. So why is graph clique in NP? Well, simply because you can guess the clique one edge at a time, or one node at a time even. Don't even have to worry about the edges. Guess all the nodes in the clique, and then when you get to the bottom of the computation tree, check that the set of nodes is a clique by verifying that all n choose 2 edges are there among the n nodes that you've guessed are part of the clique, of the n, the k clique that you're looking for. All k nodes, all connect to one another, so it's k choose 2 different edges. Make sure they're all there, and if there are, raise your hands in victory and say, I accept. Yes, it's a clique. And that's a non-deterministic algorithm to determine, a clique. So it's an NP. So we've done the second. The second part usually is easier, because almost every NP algorithm is of the form guess and then verify. How many understand when I say guess and verify what I'm talking about now? Okay, there's half of you. I'll take it. By guess, I mean non-deterministically branch across all possibilities, and find at the bottom. You have to verify, because you want to make sure that you didn't reach a dead end that is a non-answer and still accept. You don't want to do that. So yeah, you can guess a lot non-deterministically, but then you have to verify that the sequence of guesses actually work out by plugging it back and making sure it's an actual solution that you guessed your way to. You don't just guess blindly and then walk away. You guess and then verify that your guess has worked. Right? Remember, non-deterministic computation is a tree where there exists, right? There exists a path to a solution, as opposed to a for all. Right? Okay, so let's show another proof. Now we're on a roll. I'm going to show that the problem of independent sets is NP-complete. So what's an independent set? It's an anti-clique. Given a graph and an integer, is there an anti-clique, meaning a set of k nodes, no 2 of which are connected to one another. Right? So it's a non-clique. Not just a non-clique, but none of the clique edges are there. That one is pretty easy, actually. So how do you find an anti-clique? So finding a clique here is the same as finding an anti-clique in the negation of the graph, the complement of the graph. So take all edges and remove them, and non-edges now make them edges. So change edges to non-edges and non-edges to edges. Just flip all the edges, in other words. Edges disappear, and non-edges that weren't there before, now they're there. So this graph is an anti-graph of this. It's the negation of the graph, the complement of the graph, however you want to think about it. How many get that technique? So you negate the graph, and so a clique here will correspond to an anti-clique there. So for example, let's say there was a way to find out that these 4 nodes here are a clique, and there's the clique in purple. Clique means they're all connected to one another. All n choose 2 are there. Edges are there. So here's four nodes, which means 4 choose 2 edges are there. All edges are there among the 4 nodes. So that's 4 choose 2 is 6. There's all the 6 edges in purple. Well, guess what? In these 4 nodes here in the complement of the graph, none of these 4 nodes have edges in between them. There's no edges whatsoever between any 2 of the 4 nodes, simply because a clique here is an anti-clique there. So if you have an independent set solver, which is an anti-clique detector, you would be exploiting it here into being a clique detector, which we already know is hard because we just proved on our previous slide that detecting cliques is NP-complete. So now we know detecting anti-cliques, or rather independent sets, the same thing, is also NP-complete. So this proof was relatively straightforward. The next few proofs won't be straightforward at all. Yeah.
All right, here we have a pretty simple example because it's just a complement. So complementing one way is the same as complementing the other way. The inversion is pretty simple. But is that purple arrow, after you've done your optimization and now you want to go back to the original problem, is that conversion necessarily so trivial, or are there cases where you can't just take the result of the optimizer and convert it to another problem?
Yeah, so it's the latter. So here, both directions were easy, but that's a coincidence. It's a happy coincidence, to be sure. Most of the time, even one direction is hard. The other direction may not be obvious at all, even if you nail down the first one. But luckily, you don't have to go backwards, right? You just have to prove that all of NP reduces to the new problem at hand, whose complexity you're trying to determine. In this case, independent sets or anti-cliques. So this purple one is not really the reduction. The reduction is the red one. Kind of how they're related. You can also reduce it the other direction. But to reduce it the other direction, you better know that this is NP-complete first, and then you show that that is NP-complete. But we already showed that that is NP-complete some other way. So now having said all that, let me give you a more general answer. You can always find by hook or by crook the other reduction, no matter what. How do we know that? And in 2 words? Cook's theorem, yeah. Because both of these problems are in NP. All of NP reduces to any NP-complete problem. Both of these problems are NP-complete. So all of NP reduces to either that problem and separately also reduces to that problem, including the other problem, because they're in NP too. So by Cook's theorem, you can always force a reduction the hard way if you don't find an easy one like this. So I answered it 2 different ways, and so in general, you can always do that. In practice, it may not always be pretty, because Cook's theorem is a messy, hardcore reduction that is not elegant. It's brute force. This reduction is obvious and it stares at you in the face and it's nice and colorful. So you want to stick with what works more nicely, succinctly, systematically, elegantly. It's called Occam's razor, right? Yeah.
Cook's theorem only helps you with the decider, right? You still have to build the optimizer individually for each problem.
Remember, the optimizers are also in NP. So if you have a machine that's some computation, some NP computation, in this case an optimizer, not a decider, that too can be reduced into a Boolean formula. That's true if and only if that optimizer halts with the answer that it wants to spit out. But let's keep talking about deciders for now. So I don't want to muddy the water jumping back and forth between deciders and optimizers. So let's talk about deciders, because yes is mapped to yes and no is mapped to no's, and you don't have to worry about right now the dichotomy between the two. We'll come back to it if necessary. We'll circle around. I'm going to show you more NP-complete proofs at this point. So what have we done here? We've built an independent set solver from a clique solver. Okay? And of course, independent set is an NP. That's the easy part, guess and verify. And so bottom line, independent set is NP-complete. Okay. Any other questions about this for now? Transformations are tricky. In general, we've seen a few short ones. We're about to see some more complicated, involved ones that are not so easy to describe, that are take multiple slides even to describe. And let me just say that some transformations are extremely difficult. Some transformations take hundreds and hundreds of pages to describe. No kidding. People wrote entire PhD dissertations, 200 or 300 pages about a single transformation showing some new problem was NP-complete. And usually the problem is not in showing that the problem is in NP, but the problem is in showing that all of NP reduces to it. That's usually the hard part. So transformations could be very tricky. They could be arbitrarily difficult. And sometimes they're very surprising. And sometimes you look at a transformation and you say, wow, that's very, very clever. How did somebody embed all of NP in some problem that doesn't seem like it has anything to do with our non-deterministic computations, and it turns out, it does. So graph colorability, is kind of one of those, right? How do you reduce all of NP into the question of, given a graph, is it 3 colorable? Can you paint all the nodes with 3 different colors in such a way that no 2 adjacent nodes share a color, share the same color? So we can reduce it from 3 sat. So this will be the first non-trivial reduction here. This will be a tricky one. So take a deep breath and dive into this. So we're going to construct from the satisfiability clauses, the 3 clauses, so-called OR gates that look like graphs or pieces of graphs, I should say, components of graphs. So this clause here, x plus y plus z, we translate into this piece of graph, and there'll be other pieces in the graph. I'm just showing you a tiny component in this graph, and it's going to happen in a way that this formula is satisfiable if and only if whatever color the graph, whatever color in a 3-coloring this node gets, one of these 3 nodes must get that same color. So if this node ends up blue in the 3-coloring of this larger graph from which this component is a piece of, one of these 3 nodes must be blue as well. That's a property of this gadget. So we call this a gadget, but it's really just a component from which we will build larger and larger graphs that will be 3-colorable if and only if the formula that this graph sort of represent or capture is satisfiable. And so if you have a colorability decider for graphs, or even a 3-colorability decider for graph, never mind 4-colorability or k-colorability, just 3-colorability, you'll be able to exploit it into solving arbitrary satisfiability instances for you. You'll build a decider for satisfiability from a colorability decider for graphs, even though the two problems don't seem to be related, right? So why is this true? So whatever color this gets, the other 2 colors must be the blue and the green. And if this is blue and this is green, this could be, if this is blue, if this is green and this is red, then if this is green, this could be red, and so on. If you follow the colors around, you'll see that one of these 3 must be the same color as that. Now, I'm not saying that blue is the true color. It's a color corresponding to truth, and red is the color corresponding to falsehood. Because you can flip the colors around. You can say, make this color red, and then one of these 3 must be red, and now red will be the color representing truth in this transformation. Because the colors don't have to be green, blue, and red. They could be colors A, B, and C, or alpha, beta, and gamma, or colors X, Y, and Z. We can call them arbitrary names. They're just names, right? So don't get stuck on blue being true and red being false. It could be the other way around, or it could be 3 other colors. But that's where we're going. These 2 of the colors represent truth and falsehood, and the 3rd color will be neither one. And we'll see, we're not done yet. This is only the beginning of the proof. But that's sort of where we're going next. And okay, yeah, 3rd color is neither. And you'll see how that works. Okay. Now, separately from these gadgets, 1 per 3 clause in the formula, you'll have these triangles in the graph separately. Every node representing a variable will be connected to another node representing the negation of that variable, and both of these will be connected to this 3rd node. So this 3rd node will take on this 3rd color that's neither the true nor the false, because if x is blue and this is green, this must be red. So red will be false, blue will be true, or vice versa. If x was red, x naught must be blue at this point, because both are connected to this and this is green. Or the green could swap with other colors. So we have 3 colors, so every node representing a variable and its negation will be connected to each other, which means they can't be the same color, and neither one could be the 3rd color, which means they can only be the 2 colors that we will connote or construe as true and false for every variable in its negation. Again, we'll go forward and then we'll circle back, and some of this will be more obvious in retrospect, because right now it seems like magic. Like, how can this possibly work? And by the way, these triangles occur for every single variable x and y and z and w. So I'm just showing you, so I'm saying for all variables, you have a triangle like that in the graph. Okay, and separately you'll have a triangle, connecting, this green node to a true and a false color nodes. But remember, the graph is not colored, okay, originally. We're, in the process of coloring it using a colorability subroutine, but let me show an example of how this works rather than to talk more in the abstract. So let's say you have an example of a Boolean formula that looks like this. We're trying to determine if it's satisfiable. We don't know. But we have a graph colorability decider, a 3-colorability decider that works efficiently, and it can determine whether a graph is 3-colorable or not. So how can we exploit this colorability decider into solving this satisfiability instance for us? Well, here are the transformations we had in the previous slide. Every clause will create a gadget like that. And then we have these triangles that we talked about a minute ago, and then finally one triangle here. So here's specifically how it's transformed, how this satisfiability instance is transformed into a graph colorability instance. First, we'll create a gadget for the first. This is the red clause, color-coded red here. So x plus y plus z will translate into this. How many can see that this picture is the same as that picture, just slightly morphed, because graphs are about connectivity, they're not about geographic or geometric positions in the plane, right? Graphs just show a topology, a connectivity. So this is the same as that, just a little bit deformed. And the reason I'm deforming it, because I'm going to have to fit other things onto here. Second clause will give you this green gadget here. And the x and the y and the z variables are already represented as nodes in this graph, so I don't need to represent the z again, just the x naught and the y naught. And this output node t will be the same one. So they're all connected to the same output because the t is identified. This t is the same as that t. And by the way, this t here is the same as that t here on this slide too. And this green is the same as that green. There's only one node that's going to be green in this kind of triangle scenario. Other nodes may be green elsewhere. But let me just say something I haven't said explicitly a minute ago, but I probably should. This whole graph acts as an OR gate, a logical OR gate. If for the output to be true, one of the three inputs has to be true. How many can see I'm trying to construct a logical OR gate? And why OR gate? Because if one of these variables in the formula is true, the whole clause is true. And the whole clause is satisfiable if and only if at least one or more of the variables in it, or negations of variables in it, is true. So in a sense, it's an OR gate. And not just in a sense, you can see the ORs right there. It's x or y or z. The pluses are ORs. Okay, so right now we transform the second clause to this green OR gate here. And then finally the blue clause gets translated into this, again, copy of this OR construct. The y and the x naught, these two variables here, are already in there, so I don't need to add them again. The z naught is new, so I'm adding the z naught over here, which is that z naught in the third clause here. And of course, they're all connected to the same output node t. So I've constructed these three OR gates graph-wise from this formula in this manner. Right? And here are all my variables, x and y and z, and x naught, y naught, and z naught. Every variable will appear once on this left-hand side row where we have the variable nodes. Okay? And that's the third clause, represented as a graph OR gate equivalent. Now, I'm going to take these two nodes, the green and the red. So I'm taking these two nodes from this triangle here, and literally I'm placing them here and here for convenience. But I'm going to create this purple triangle now along this, between this green node, this blue node, and this red node. And remember, they're not colored yet. I'm showing you what the colors would be in a three-coloring if we three-colored it. But I'm not committing to these colors yet. I'm just kind of depicting them diagrammatically, notionally, to kind of show you where it's going. And there's the purple triangle. How many can see that this purple triangle here is just a deformed version of this purple triangle? Graph-wise, they're the same. Geometrically, it looks very skinny, long, deformed triangle, but still, topologically, it's the same connectivity. So they're identical, they're isomorphic. Right? Okay, now I'm going to create all these triangles. For every x and x naught, I'm going to create a blue triangle here in this graph. So I'm going to connect the x to the x naught and the z to the z naught in a triangle like this, and both will be connecting to this node here. That's the designated green node. And you ask what the green node is. It's like this big master node that's kind of on the left-hand side. There's only one of them. Of course, other nodes inside here could be green later, but that's kind of the green anchor connecting to every node and its negation, which means a node and its negation cannot be the same as each other in any three-coloring because they're connected, they're neighboring. So if z gets blue, z naught must get red, and vice versa. So these triangles ensure the constraint that variables and their negations get opposite values in terms of colors, because they have opposite values in terms of truth values, true versus false. So these triangles will occur between any variable and its negation. So x will be connected to x naught, and both will be connected to the green node, just like it says so here. Y will be connected to y naught, and both will be connected to the green node, and so on. So I have an entire graph now that captures this formula in the sense that for whatever color this, if I three-color this graph, whatever color this node gets, one of these three inputs to this logical OR gate that is represented as a piece of a graph must get the same color. Also, it ensures that no node and its negation get the same color. Not only that, both of these colors will be different than this node here, which we'll designate as the green node. So in some sense, this graph with respect to colorability represents and captures this formula with respect to satisfiability. How many can see that? Good, that's, third of the class, I'll take it. It's a subtle interaction, it's a subtle reduction here. Bottom line is, if I can find you a coloring here, so now I sent this to a coloring optimizer, and it's giving me the coloring. So if I have a way to infer the coloring here, automatically I get a satisfying assignment here. How? Just check which colors are the X's, the Y's, and the Z's. Blues or reds, and blues represent truth, and red will represent falsehood. So this three coloring will give us immediately a satisfying assignment. For example, the one right there. And it will give us a solution. For example, X is true because it's blue, Y is red, false. Z is red, false also. And if you plug it into the formula, you'll see that satisfies the formula, right? X is true will satisfy the first clause. Y is false will satisfy the second clause. Z is false will satisfy the third clause. And the rest don't matter. So what have we done? We've converted an instance of satisfiability that came in the door, an arbitrary instance of satisfiability, into a contrived, cleverly constructed instance of graph colorability in such a way that this instance of graph colorability is three-colorable if and only if the original formula is satisfiable. And that's a reduction of satisfiability to graph colorability. So if you have an efficient solver for colorability, here's how you can exploit it into being an efficient solver for satisfiability. So all of satisfiability reduces to colorability, and all of NP-completeness reduces to satisfiability already. That's Cook's theorem. So thereby, all of NP reduces to graph colorability via the composition of these reductions. Cook's theorem to reduce all of NP to satisfiability, and then this thing here that reduces satisfiability to graph colorability, which makes graph colorability NP-complete after we show it's an NP, like he said earlier. So what makes graph colorability in NP? Guess a coloring, node by node, and at the end, check that the coloring makes sense, that no two nodes are adjacent, have the same color, and that puts it in NP. I just gave you an NP guess and verify algorithm for colorability. So now that colorability is in NP, and all of NP reduces to colorability, that makes colorability NP-complete. End of proof. So that took, that took 2 slides, and 2 dense slides, and quite a bit of insights to see that this works. And by the way, this reduction here of satisfiability to colorability, that's a polynomial time reduction. We have to also mention that. Why is it polynomial time and not exponential time, where the graph blows up exponentially, in the size of the formula? How big is this graph in terms of the size of the formula? The formula is n variables. Roughly, how many nodes will the graph have? It's not a trick question. It's pretty straightforward. But let's just nail down the proportions here. Just asymptotically, big O, I don't expect, the exact constant, although we'll talk about the constant next, just for the heck of it. Big O, how large is this graph as a function of this formula? If the formula has n variables, roughly, how big is the graph? Be order n. How many see that? It's just linear in the size of the formula. Why? Because every variable here will end up with a node here. These gadgets all have 5, 6 nodes in them, but there's only 1 per clause, right? So it's, there's as many gadgets here as there are clauses. Each one is constant size. It's not growing arbitrarily, right? And these just 1 more node, 2 more nodes, 3 more nodes. Okay, so a few more nodes. There'll be a bunch of edges, but there are no more edges than the square of the number of nodes. And in this particular graph, the number of edges is not even the square of the number of nodes. How many edges are in this graph as a function of the number of clauses in the original formula? Take a wild guess. Big O, How many say linear? Yeah. Any issues with the graph being linear in size, both in edges and nodes, as a function of the original formula? What if it was quadratic? What if the size of the graph was quadratic in the size of the formula? Would that be terrible? Will the proof still hold? How many say will still hold? Yeah, why? Polynomials. It's all polynomials, right? We just care about this is a polynomial reduction, not with the degree of the polynomials, but just for the heck of it, it's not just polynomial, it's linear. The degree of the polynomial is 1. It's a linear polynomial, it's not just a polynomial. If you want to talk about the constant, it's roughly, each variable will have 2 nodes here, and each clause will have 5 nodes here. That's a constant 3 number of nodes. So it'll be like 5 times the number of clauses and 2 times the number of variables, roughly, whatever. It'll be a small constant times linear if you want to bicker about the constant. But none of that matters as long as it's polynomial, and it is clearly a polynomial. So it's a polynomial transformation. This transformation that we described here is this f from A to B. How many get this abstraction? Remember A, B, F, mapping members to members, non-members to non-members? How many remember that slide? We showed it many times. All right, this is an instance of that slide. What is A and what is B here? Just to map this abstract slide into this concrete example to kind of nail it down, let's just connect the two. Yeah. Yeah, A is a bunch of satisfying assignments, let's say as strings. B is a set of all 3 colorable graphs, represented as however you want to represent it. Long strings representing adjacency lists and whatever. Yeses map to yeses and no map to no's. Satisfiable formulas map to 3 colorized graphs, and non-satisfiable assignments or formulas map to non-colorability graph instances. Graphs are not 3 colorable. And the F, this mapping, is this process of converting a formula here to a graph there. Okay, so you might ask, so how many understand at least the gist of it? Not necessarily every last gory detail. Okay, we're in deep waters now. Transformation-wise, this was not a non-trivial transformation. I mean, think about the cleverness it took somebody some 45 years ago, because this happened in the early 70s, to realize that you can convert a Boolean formula into a graph in such a clever way that the formula is satisfiable if and only if this resulting graph is 3 colorable. I mean, that's a lot of cleverness. Because graphs and formulas don't look the same, don't smell the same, they don't sound the same. Graphs are not Boolean formulas. Boolean formulas are not graphs. Graphs have nodes and edges. Boolean formulas have ands and ors and variables. I mean, how can you solve one type of animal using, a solver for the other type of animal that looks nothing like the first? Well, this is how. This whole thing is about transformations, reducing problems to other problems. Okay, so you might think that so what makes colorability hard? So I give you a graph like this and say, paint it with 3 colors, go. Why should it take exponential time? Certainly it won't take any more than exponential time, because you can try all possibilities, exponential number of potential colorings, and some will work and some won't. But why can't you do it quickly? And maybe it's because the degree of the graph is very high some places. Notice that the degree of this graph was pretty high over here, and it was pretty high over here, and potentially elsewhere. But why, maybe it's a degree that being high that makes it hard. Because if the degree of a graph, the maximum degree of a graph is low, the problem becomes much easier. If the degree of the graph is everywhere 0, and I ask you, is a graph 3 colorable? I give you a graph of maximum degree 0 everywhere. What is your algorithm to determine if it's 3 colorable? Just say yes, you'll be right. How many get that? Okay. Next, degree maximum is 1 anywhere in the graph. I ask you, is it 3 colorable? What's your algorithm? Say yes. Yeah, absolutely. One-line algorithm. What could be better than that? Okay, next question, less trivial. If the degree everywhere was 2, at most, the degree could be either 0, 1, or 2, but no more than 2 anywhere in the graph. I ask you, is this graph 3 colorable? What do you say?
Check your neighbors and then take the ones that are not. And if you do that, you'll see that it's your neighbors max.
You have 2 neighbors max, true. So check your neighbors and then what? Let me ask you a slightly different question. What do graphs of max degree 2 look like? What's their structure? Can you have arbitrary graphs or, you know?
It's either a linked list or a loop.
Other lists or loops? How many see that? Or disconnected nodes, those are degree 0. Right? So, but if degree is at most 2, you can have a loop or you can have long lists. Can you have a binary tree? Can you have, you know, trees that have 2 children and that kind of thing, binary trees? Maximum degree 2? No, because that's a degree 3. If you have a node that has a parent and 2 children, that's degree 3 right there. You know? So you cannot have trees. You can only have lists or loops. Is every list 3 colorable? Let me say yes. Yeah, in fact, more than that. Every list is what colorable? Not just 3. Every list is 2 colorable. How many see that? Just alternate. Red, green, red, green, red, green. You don't need a third color, blue. Loops. Are loops 3 colorable? How many say yes? Are loops 2 colorable? How many say yes? A loop is 2 colorable if and only if what is true? Odd or even cycle around the loop. How many see that? Even cycle is 2 colorable. Odd cycle, 3 colorable. And that's an if and only if. But all loops are 3 colorable. All lists are 3 colorable, in fact 2 colorable. So all graphs of max degree 2 are 3 colorable. How many understand that theorem? Okay, we just proved the theorem. Max degree 3 is more complicated. Max degree 4, NP-complete. Which is amazing, because you see how when we reduce a degree enough, it becomes trivial. Degree 0 was trivial. Degree 1 also trivial. Degree 2 was not so hard either. Degree 4, nobody knows how to do it efficiently. It's NP-complete. We're about to prove that degree 4 max graphs are NP-complete. Okay, so it's not about the degree. So we're about to prove this theorem. Max degree 4 graphs are NP-complete. And we just proved the other 3 theories. 0, 1, and 2. We just went through those 3 examples. All right, here's why degree 4 graphs is NP-complete already. And of course, any higher degree is NP-complete too, as a max. If you get NP-complete on the low end of some restriction, of course, you lift that restriction, it doesn't get any easier, it's just harder, right? Because it subsumes all the other ones. All right, we produce a gadget that has the following properties. It has max degree of 4. You can see no degree here is more than 4. Like right there, for example. The gadget is 3 colorable, but not 2 colorable. It's not 2 colorable because it has triangles. A triangle is an odd cycle. An odd cycle is not 2 colorable, but it is 3 colorable. So it has a 3 coloring, but not a 2 coloring because it's full of triangles, like this one, for example. And there's a 3 coloring of it, for example. There's others too. In any 3 coloring, all corners get the same color. How do you prove that all corners get the same color? Well, you follow the color propagation constraints, and we will do this next time because we're running out of time. But once you have this gadget with these 3 properties, that the max degree is 4, it's 3 colorable but not 2 colorable, all 3 corners, this one, and that one, of each triangle like that, each of these gadgets have the same color. What you can do is replicate this gadget multiple times, and this compound gadget has the same 3 properties. And once you do that, you can take a high degree node in a graph and reduce it to using this gadget internally. Instead of this node, you replace this node with a high degree with this gadget and keep these edges intact, and you reduce the degree from arbitrary high degree to max degree 4, and it retains the same colorability property as before. this new graph is 3 colorable if and only if the previous graph with the higher degrees was 3 colorable. And therefore, if you have a 3 colorability solver for max degree 4 graphs, you have a 3 colorability solver for arbitrary degree graphs, which will make the problem of max degree 4 colorability NP-complete as well. And next time we'll show something even weirder, that planar graphs are also NP-complete in terms of their colorability. All right, see you next time. Good, thank you.